Hello everyone. After knowing the general mechanism of the aromatic substitution, electrophilic substitution reaction, we will now do the halogenation. This is also the example of electrophilic aromatic substitution reaction. Halogenation in which the benzene reacts with the chlorine or the bromine in the presence of Lewis acid. And we get the product halogenated benzene. Now, what are the typical? We mostly use Lewis acids that are the AlCl3, FeCl3 for the chlorination, and FeBr3 for the bromination. Now, how can we prepare the Lewis acid? We can see that simply by adding the halogen into the iron, we will form the iron halides that are the Lewis acids. Now, why we use the Lewis acid? Lewis acid actually, as we have discussed earlier, that for the electrophilic substitution of the aromatic system, we need a strong electrophile. So this Lewis acid will make the halogen a strong electrophile, like as we can see. Here we have the two simple equations of the chlorination and the bromination of the benzene ring. When the benzene reacts with the chlorine in the presence of a Lewis acid, the room temperature or 25 degrees centigrade, that is usually, will give us the chlorinated product of a benzene along with the removal of the HCl. In the same way, when we see that benzene reacts with the bromine in the presence of the Lewis acid and some amount of the heat, it will produce the brominated product of the benzene. Now, before going to the mechanism of these halogenated products, halogenation, we will see the review the electrophilic reaction mechanism. That is, first, what happens that benzene behave as a nucleophile and it will attack on the electrophile. That electrophile is basically the partially positive and this was the partially negative. It will attack on the electrophile and electrophile will attach on this. This is called the arenium ion. As we have discussed earlier that arenium ion is stable ion. This is not a transition state. This is basically the intermediate that is stabilized by the resonance. And in the second step, the negative anion of this molecule will attack on the hydrogen. It will accept the hydrogen and regenerate the aromaticity of a molecule and along with the removal of a molecule. Now we will see about the halogenation of the first the chlorination and after then the bromination. Okay, fine. We will do the mechanism here. First of all, what happens that in the step number 1, FeCl, this is the partial positive, partial negative. This will then attack on this. As this is the electropositive, this is the electronegative, it will attack on the electropositive. So this situation will arise. This will make this Lewis acid now make this chlorine more and more electrophile. In second step, benzene will attack on this electrophile. This will attack on this electrophile. Now we will see that here one of the carbon electrophile will attach on one of the carbon atom and its valency will be satisfied, because here also we have the hydrogen. We have the hydrogen here, electrophile, and this carbon now contains the 4 complete bond, 1, 2, 3 and 4. But this carbon atom is not fully satisfied with this valency. We can see here we have the 3 bond, 1, 2 and 3, so it will have the positive charge on it. Now in further steps, what will happen that FeCl3 and Cl, this is the negative portion, this will abstract this proton and this bond will come over here, and it will then stabilize or regenerate the aromaticity of the molecule, and we are ended up with the chlorinated product of the benzene. Now we see that this is the arenaceous ion, and this arenaceous ion is resonance stabilized. Here we have the two steps in the halogenation. In this electrophilic reaction, what happens that first this benzene that behave as the nucleophile will attack on the electrophile, and this step is a slow step, and this second step is a fast step. Why this is slow step? Because benzene is a very much stabilized molecule, and so to attack this is to disturb its aromaticity. Basically, in this step, its aromaticity is lost, and for the aromatic system to lose its aromaticity is very much difficult. So that's why this step is a slow. Now we were talking about the arenaceous ion. The arenaceous ion is the resonance stabilized. How it is the resonance stabilized? We will now make its many different canonical form. Here we have the chlorine, positive charge, and the two double bonds. Now what happens? This double bond, both of the electron move over here. It will satisfy full of its valency between these two carbon atoms, but the valency of this carbon atom now is not satisfied. So this carbon atom will have a positive charge, chlorine will be here, and this. Now both of these electrons, this pi bond will move over here, because we have a p orbital, empty orbital parallel to these pi orbitals. So these electrons have the space to move over here. So they move over here, and it will further resonate. Now we see both of these carbon atoms are fully satisfied because their valency is full, but this one carbon atom now have the electron deficient, or its valency is not fully filled. So now this will have the positive charge. These are the basically different canonical forms that stabilize this arenaceous ion. Okay, we was talking that the water product yield of the bromination is low. This is because the bromine atom is less reactive hydrogen abstraction agent than the chlorine atom, as reflected by the higher bond energy of the HCl than the HBr. This is basically the reason behind that why the yield is high. Now we will move toward the mechanism. Okay, this is, as we know that this is the electrophilic aromatic substitution reaction. First of all, we know that here we have the lewis acid and this reagent, lewis acid and the chlorine or the bromine will react in the first step. In the step number 1, in step 1, the bromine, as we're talking about the bromine, this is the partially positive, this is the partial negative because of their size and their movement. And this molecule is the dipolar, and it will then attack on this electropositive species, and it will then form the adduct, that is bromine, and here this bromine FeBr3, and this is getting the positive charge, and here this is getting the negative charge, and this species now make this bromine atom is more and more electrophilic. That is, we said that for the bromination or for the electrophilic substitution reaction, the aromatic system, the electrophile should be very strong. So Here we have a strong electrophile. Now in the step 2, benzene, the pi electron of the benzene attack on this bromine, and both of these electrons will move on this bromine, stabilizing this atom. As we can see here, that this Br and 3 negative. Okay, this pi electron attack on this because it is now electrophilic, and both of these electrons will move on this bromine, making it stabilize, and as a result it will then form uranium ion that we already know that is stabilized by the resonance, and this species is also removed. Okay, this is resonance stabilized, so we can draw its resonance or the calculus structures. These two will move over here, and the carbon will then become the electron deficient, having the positive charge. After that, these electrons will come over here, and it will then form another conical form that is the resonance form, making it stabilize. Okay, now in the step 3, what happened? As we said that any nucleophilic species now then accept that proton attached to the carbon atom bearing the electrophile. Now that bromine, this negative charge, when both of these bonds come over here, this bromine then having the negative charge, and this bromine along with this negative charge attack on this hydrogen atom. This hydrogen atom will leave, and both of the electron of this bond will become the part of this ring system, regenerating or regaining the aromatic system, aromaticity of the compound, along with this HBr formation, and we are now provided with a catalyst is regenerated. This is basically the process of halogenation mechanism. So now what about the fluorine and iodine? The fluorination of the benzene is a very rapid process that does not limit to a single monofluorination. It will undergo the multifluorination. So some sort of the special conditions or apparatus is required, or that is in even that case it is not possible to get the monosubstituted fluorinated product. So we can do the fluorination by the indirect method. And in the same way, the iodine is unreactive, but there is also a way, an indirect way in which the iodination take place, that I will discuss in my any other video. Do share and subscribe. Thank you.